Welcome to the circuit. Uh, I have not been in the lab since 2020, but let's break down some engineering from the 2020s. So I did not study integrated circuits, but we got to know them because an integrated circuit. Now, what is an integrated circuit? Uh, Based on some Googling, you got like 7 different types. Let's see. So you got an analog and a digital integrated circuit. You got a power management integrated circuit. You got an RF integrated circuit. And you got mixed signal integrated circuits. So these integrated circuits, I don't know what the fuck they are, but essentially they work with an analog electronics, so that'll be regulating the voltage. Like amplifiers as well, that's pretty neat. And if it was an RF integrated circuit, then you got high frequency AC signals, which are analog, but they're high frequency. So your amplification comes from transistors. Now, do those also amplify regular analog signals? I'm not sure, but do they? Yeah, amplifiers and op amps and shit like that. So you got your analog circuits, which are just like voltage AC waves, DC signals, and the power management integrated circuits, which are like power management is like how much power, so voltage and current. It depends on your sources and how much power you want to send from one source to another. Now, I heard that was done by power converters, which I did not study, but that's what works with integrated circuits. So basically, what I'm saying is, let's dissect some boards. This and enough mumbo jumbo, and let's dissect some boards. So you see here, diddly dally do ha. These are integrated circuits. Now, this shit is the chip. I don't know what the fuck is on this chip. I'm still not too certain. But I know these pins, now you solder them, which means you take a little bit of hot iron, hot lead, and you mold them so this metal rod connects to the metal part of your chipboard. Now, what is a chipboard? A chipboard. Where's a chipboard? A chipboard is like this thing. So you see here, you would need these little lines are metal. And the green stuff, well, parts of the green stuff are where it's dielectric, so no electricity can flow. So electricity flows at the speed of light on these fucking gold parts, all right? Now, apparently, these gold parts are not just paths for the electricity to flow, but you would also attach to them resistors, capacitors, inductors, diodes. What do those do? And transistors, what do those do? So they can amplify the current between two parts of connections. They can modify the level of the voltage and the amount of power going between two parts. They can also process and read the signal. So if it's an encoded message, analog message with varying voltage and frequency, they can encode that and decode that with filters. So filters use capacitors, inductors to change the bandwidth of a signal. And then rectifiers and oscillators, I believe, read the fucking voltage levels. So like you read the voltage level and the frequency to understand what a message is. And you can change that with your little IC chip into a analog to digital, which now becomes ones and zeros. So now you work with a computer and you have ones and zeros. And what do those ones and zeros do? Those ones and zeros are on a clock-based cycle, 4 gigahertz, right? And those are RF levels, RF frequencies, speeds. And you get to do things like write code. You get to read code. You get to read messages. You get to send messages. You get to access data. So it says where on the chip to access your data. So if someone had access to your chip, they could access your data. All they got to do is find out where the fucking memory is and read the memory. So you got your little computer here with ones and zeros, reads the memory, takes the memory, stores, changes data, does mathematical computations, does processes, and just with ones and zeros runs a computer with many of these chips and shit like that. And you got analog signals if you're doing an antenna, a GPS, a Wi-Fi. You got radio frequency, so you're amplifying the signal. You got your little message that you're gonna send out over Wi-Fi or over the internet or over cellular line. So you have your little message, you have your little microphone, you have your little microphone speaker, you talk into it, and it goes onto the chip. It turns into an analog signal. It gets encrypted, and it gets encoded. And we power amplify it, and we broadcast it from the chip using electricity to go across the airwaves. It comes back, we decode it, your receiver decodes it back into an analog signal through the little speaker, and you hear the other person's voice. So that's how you work with analog RF signals and shit like that. Analog signals. That's basically all the shit you do, It's a fun time. Let's go with this one. Now this was a little diddly-doo-ha. This is what I'm talking about. This is some kind of resistor. It's a big resistor. These are little resistors. These doohas are capacitors. Capacitor. Or maybe I think this is an inductor. Yeah, this is an inductor. And these are resistors. And this is a capacitor. So you got little capacitors to filter out DC signals. So you're filtering out like DC and allowing AC. So you're changing the bandwidth of high frequency signals, low frequency signals. Inductors and capacitors do that opposite of each other. One is high frequency, one is low frequency, because it allows an AC signal or it allows a DC signal. And you use them together and you get your bandwidth. Bandwidth is how much range of the frequency spectrum you can process. Sometimes you want more bandwidth, sometimes you want to filter out selective ranges of the bandwidth, but you want to preserve the intensity of the signal, right? These are our little integrated circuits. They got the little 8 4x4 connections. Now for this board, like these vertical connections are connected in a line all across one node. So you plug into the line all across the vertical side. And these where the blue and the red are connected this way. So you plug in here, blah, 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 and then you plug them in here, blah, 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 and then these power up to where you want. Do you want it here? Do you want it on this line? Do you want it on this line? So these are external power supplies, AC or DC signals. You know, like black is ground, yellow is live, black is ground, red is live, and shit like that. Or plus 5, minus 5, plus 15 millivolts, minus 15 millivolts. And you power up the back of your board, so it powers up the back of the board. And all you do is you connect your little your circuit shit. So you build your circuit to communicate with itself. And then whenever you want to connect to a power supply, you just connect a little cable back into this line or back into this node, which connects to your function generator connecting from these power supplies. And this little circuit communicates with itself. It modifies shit and it acts like a program. So every circuit you see is kind of like a computer program because it does some shit. It does some shit. Now this little guy right here, this little guy is a mic. So you speak into there. And there's no way to read it. We don't have a speaker here. Or is that a speaker? That's either a mic or a speaker. I'm not sure. So you would get a signal. It either goes into there, and we process it with these filters we got going on, with these resistors we got going on. We don't got any transistors though, so we're not amplifying the signal anywhere. Although we got these guys, maybe these guys amplify it as well. I'm not sure. Those are the integrated circuits. Like each one of those ports is connected to a different part inside this chip, which does something else to the fucking port, some other command, some other feature. So that's basically how you build. Now this little shit is the exact same shit that happens in here. You just take all this shit and you use miniature nano size chips, like chips that are this big, have billions of these circuits. So this is a circuit exploded for a laboratory work to see what the fuck goes on. But this exact same shit happens on a nanoscale. You get billions of these using very tiny processed and fabricated resistors, capacitors, inductors, filters, transistors, amplifiers, and you process signals like that. And you in fact turn your computer software code into computer hardware code with these circuits. Now the only pain in the ass is debugging them. You know, that sucks because you know something should just burn to pieces. You don't know what the fuck went wrong. This is our RF technology. Now this could be like a Wi-Fi modem or something, you know? So why is it special? Because it's super high frequency. In fact, we do have transistors. Now, transistors in RF technology means there are some reflections. So if you don't balance it out, why is it so big? Why is it so fucking big? The reason it's so fucking big is because it's RF technology. So the AC signal really behaves like a wave on here, and waves reflect back and forth. So if you make it bigger and design it how big you want, you know the strength of the signal coming in. You know the strength of the signal coming in. You know the bandwidth you want. You know the frequency. You know the amplification. And you know what your desire on the output is. Right here on the output, you know what you desire. So you build it so the impedance is matched. So the front part before you amplify it matches the resistance, the impedance of the back part. And if the impedance is matched, you get ideal power transfer and you get no reflections and nothing blows up. Your components don't burn to pieces because it's not mismatched. So that would be for high frequency signals, like in the gigahertz. Normally these little circuits, I don't know if they're gigahertz, but they would need this shit as well. Why is mine so big and they're so small? Maybe because we use more power. No, I don't fucking know. Well, the natural impedance had to be 50 ohms. Maybe that's why ours is bigger than theirs. I'm not fucking sure. Like we were powering 16 volts, I believe. I don't know. But that's a fun time. It's a fun time. Now you plug these into some scopes. You got these devices where you're going to plug these. You're going to plug attach a thing to the end port, attach a thing to the front port. You got your signal coming in. And you measure like how much reflections, where you can use an oscilloscope and actually touch the part of the circuit you want. You can connect and touch parts of the circuit to see the voltage reading there. And you on your screen on your device, you get like a sinusoidal wave, or you get a square wave if it's digital, ones and zeros, and every one is 2 volts, every zero is 0 volts or minus 2 volts, and you get like a square wave. and you see where your wave is expected based on your calculations to actually match what the fuck's going on in your built-in design. And yeah, I didn't go into fucking any details like what the actual filter does, how actual you convert digital to analog signals, how you actually process them, because that's all math, and I don't fucking know about the math. I can learn it, but just off the top of my head, I don't know what the fuck the math does. But on a higher level system, that's just a little voodoo magic of what the fuck goes on in a little circuit and how it behaves like a computer program. This is power amplifier, kind of like a power amplifier. So you're just basically you're conserving the integrity of the signal. So the signal is not changing. It's being the same, just being amplified. So it can be coming from a receiver, like you're downloading something off the internet with Wi-Fi, with your cellular network, and you receive it, and you amplify it, or then you gotta lower it. And then you process it, and then you get a signal which your little ass chip can handle. Because if you get the big ass signal and you put it onto your little chip, it's gonna burn everything apart. So you need to manage power. Power management is one feature of this entire fucking thing, just to do that. And this thing does all the calculations like a computer program. And that's basically one of those guys, just on this big ass board. So basically, it's a fun time. It's a fun time. You got diodes as well. Now, diodes, capacitors, inductors, resistors. You got your little wires connecting to your supplies, your DC supplies, your AC supplies, your current sources, your voltage sources. And it's a fun time. Then you got your transistors and your ICs. And in the schoolwork, we learned to design the actual circuit using transistors. This wasn't my specialty. Maybe it was. I don't fucking remember. I don't know. So you would build a circuit using the transistors, resistors, and you would know like that's a current match, current source, current mirror, current matching. And that is this type of amplifier. And that's a mirror. That's a feedback loop. So that one does feedback. And then you would use a transfer function and control system technology to regulate when shit goes wrong, when the signal changes, how does your output change based on the feedback loop and what your computer is, what your regulator is commanding your output to be and how quickly it matches. So you got control systems, transfer functions. And that's a fun time. That's all you fucking do. It's a fun time. It's a fun time as an engineer. On the low power side, that's low power. That's making your little cell phone chips, your computer chips, your TVs, your computers, your radios, MP3 players, tablets, laptops, computers, desktops, cellular networks. That's your low power. Then you got your high power shit, which is like transmission lines, big ass satellites, antennas, radar stations, base stations, power generators, turbines, electrical generators, electrical power, big ass transformers. And that's where you got your big ass power, and you got hundreds of kilovolts of power or megavolts of power. And you got low frequency for that. Big ass cables, big ass transformers, turbines, generators. You got magnetic induction, magnetic electric induction. You got electromagnets, motors as well. So big power is also your electric motors for machinery and vehicles and jet propulsion motors, where you need your electric power. And that could be a motor powered by a DC motor, powered by an AC motor, which our friend Nikola Tesla gave us. It could be an AC synchronized motor, an AC asynchronous motor, if that even exists. Probably not. Probably only got synchronous motors for AC. And that's it. It's fun time. It's fun time. What else you got? Then you got your software shit, right? You got your software. So you write your code in your different programming languages, and you work on what the computer actually sees in the memory it reads, in the security and the all the data it stores and reads and regulates, and the databases. And you got your communications and front end design, back end design for your software code. And that's it. That's it. What else you got? It's a fun time. It's a fun time. It's a fun time to be an electrical engineer. It's a fun time. It's a fun time. It's a fun time. It's a fun time. What else? I don't know. You got your lights, lighting. It's fun time. 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 You got analog technology, like you're trying to communicate with airplanes and radars and radios, and trying to see at an antenna radar station where the airplanes are landing and shit like that, and the control tower, or the radar for the military and missiles and aircraft and submarines and warships. And you use your analog technology, which doesn't have any computers and shit like that, and just fucking find out using physical built ass devices to act like computers. That's like this shit that I showed you. These shits to act like computers and tell you data that you need to know about where communications between aircraft and shit like that. Or you can do it digitally, where you get a computer to tell you where the fuck the info you want to know. And that's about it. We just summarize all there is to do. There's nothing left to do. What else can you do? What else do you do? You got the math, you got your calculus, you got your physics, right? And that's the fun time. That's the fun time. That's the fun time. Then you got your mechanical engineering, who build the cars, who work on the engines, who work on the vehicles, the suspension, the speed, the velocity, the nuts and bolts and wheels and gears and shit like that. Then you got your chemical engineers, who work on the fuel and the oil and shit like that. Then you got your nuclear engineers, who work on the nuclear power plants. Then you got your civil engineers, who make the buildings and the bridges and the dams. And then you got your lawyers, who sue everybody and work on the legal side. Then you got your doctors, who heal everybody when they bust up themselves. And then you got your bankers and your finance people to finance everything and manage the debt. Then you got your Hollywood executives to make movies and actors and films and sets. And it's a fun time. It's a fun time. So, study something, learn to do some shit other than post on social media. Anyone can fucking post on social media. Even if you get $1 million, you're still a douchebag. You're still a fucking douchebag. So, study something, become a professional, and learn to do something. Even if you're a professional yoga instructor, at least you're a professional something other than a douchebag on Instagram. So learn to do something, become an expert, and it's a fun time. It's a fun time. Stay classy, New York.